Alrighty, this is the video for Electromagnetic Induction for the Garza School of Physics, Chapter 25. We've just got this one more, and we're almost at the end of the year, so congratulations. We learned last chapter that you can use a magnet and a wire to cause a force on the wire. So if you put a current-carrying wire into a magnetic field, there'd be a force on that wire. So we know there's some kind of interaction between magnetic fields and current-carrying wires. And we learned that if you turn a current on or off in a wire, it creates a magnetic field. So the question then is, well, can we do this in reverse? Can a magnetic field then create current instead of current creating the magnetic field? And as in physics, usually things are symmetrical, or maybe always things are symmetrical. And so the answer is going to be yes. You can use magnetic fields to actually generate current in a wire. So we'll see how that happens. It's called electromagnetic induction. Induction, again, just if you think back to the word we used in static electricity, it means to cause something to happen. So like an induced dipole, we caused a dipole to happen. So we're causing electromagnetic current, in this case, to flow. So it's called electro because it's current flowing, but it's called electromagnetic because it's caused by a magnet. So it's a combination of electricity and magnetism kind of merging together as one overall topic. So the required thing that's critical in order to get current to flow in the wire is that the wire has to be moving through the magnetic field, or relative to the magnet. So if you just hold a magnet and a wire next to each other, both stationary, there won't be any current flowing through the wire. But if you move the wire across, back and forth, or near or away from the magnet, then current will flow through the wire as long as the wire is moving. So to try to visualize why this makes sense, it actually is something that we already could have figured out based on what we learned in the last chapter. So we learned that if there's an individual charge moving through a magnetic field, there's going to be a force on it, and we use the right-hand rule in this formula QVB sine theta, and we had this right-hand rule triad, direction the charge is going, magnetic field, and force on the particle. And so you could figure out the force on any given charge moving through a field. But when you take an entire bar, metal bar, or a wire, and you move that through the field, every single little electron that's in that wire is a individual electron moving through a magnetic field, and it's going to feel a force. So what happens is, in the wire, all of the, say, positive charges feel a force in one direction, all the negative charges feel a force in the other direction, so the positives will start going one way and the negatives will start going the other way, which generates a current in the wire. If you want to think of it as just the positives moving one way, just the negatives moving the other way, or actually a combination of both of them moving, in any case, that will create a current in the wire. And if you hook the wire up to a light bulb or some kind of circuit, then the current can flow all the way around. If you just have a single metal bar that doesn't have anything connected for the current to make a closed path, the charges will move to the two ends, which will then actually create an electric field because you have a charge separation, positive on one side and negative on one side, and that will create an electric field with a force in the opposite direction, and it will come to equilibrium so the net force on all the particles is zero. So that's also kind of cool. Anyway, so it creates a current through the wire. So if you want to visualize this, say we've got a wire, and say we're going to move the wire this way. So let's say the magnetic field is going into the page. And we're going to move the wire this way. So imagine you're this little positive charge right here inside the wire. So I'm just going to do it here. The velocity is up, the magnetic field is into the page, so the force is to the left. So there's going to be a force on positive charges. So what's going to happen is, as this wire moves upward through the field, you're going to have positive charges building up over here, and then electrons are going to move the opposite direction. Negatives will build up over here. And again, if you were to connect this together, with some kind of resistor or light bulb, the charges might actually be able to flow all the way around. Or alternatively, you'll build up a net positive charge here and a net negative charge here, which then is going to create an electric field inside. And this E field puts a force in the other direction, and the created E field inside will be the exact right magnitude to perfectly balance out this electromagnetic force, trying to push them, say, positives to the left in this case. So that's the effect of moving a wire through a magnetic field. So you might want to know, well, how much current is going to flow? we know that some charges are going to move this way and some charges are going to move that way, but how many, at what rate, etc. So we can calculate exactly how much is going to flow, and there's going to be 4 things that it depends on. And this is a result of that QVB sine theta formula, just kind of taken on a macroscopic scale for the entire wire all at once. So instead of looking at how much current flows, because the amount of current that flows depends on what resistors you hook up to the circuit, but instead we'll look at how much voltage is created across the wire. So the stronger the magnetic field, the more voltage you'll get. The longer the wire, the more voltage you'll get. The faster you move the wire, the more voltage you'll get. And then sine theta is telling you that it'll maximize when theta is 90 degrees. So you want to move the wire perpendicular to the field. If you move the wire parallel to the field, nothing will happen, just like if you move a charge parallel to the field, there won't be any magnetic forces on it. So sine theta is the angle between the motion of the wire and the magnetic field. Okay, so if you multiply the magnetic field by the length of the wire times the velocity that you're moving the wire times sine of the angle, that'll tell you the voltage induced between the 2 ends of the wire. So basically, when you move a wire through the magnetic field, the wire itself turns into a little miniature battery based on how strong the field is, how fast you're moving it, and how big the wire is. And then the amount of current is, of course, just based on what you hook up to it. If you hook up a light bulb with a certain resistance, then you can use, obviously, V equals IR to find the current. Okay, so this induced voltage, it has a poor name that came from a long time ago. They called it the electromotive force, or EMF. It's not a force, absolutely not a force. It is a voltage, but it kind of makes sense why they would have named it an electromotive force, because it does cause a force on the particles. So it makes the particles move, and it only happens when you're moving the wire and it's creating electricity. So the name kind of makes sense based on what they would have known back in the early 1800s when they were doing these first experiments. But now that we've kind of got a more full understanding of electricity, magnetism, current, voltage, etc., we want to call this a induced voltage, not an EMF or electromotive force, because it's not actually a force. Okay. Last thing is, to find the direction that the current is going to go, apply the right-hand rule for the charges. So just like I did this previous slide, imagine your entire wire moving, imagine you're a positive charge inside, and use your velocity, magnetic field, and force right-hand rule triad to determine the direction that the current is going to go. The direction of the current or charges will move in the same way that the direction of the force is from your right-hand rule. Okay, so how can we use this? Instead of having to actually take a wire and move it in a magnetic field to create current, what can we engineer some kind of device that will do that for us? And the answer is, of course. So we want to move these wires in the magnetic field, but you can't just keep moving the wire forever because you're going to run out of space. You know, your magnetic field is constrained to being nearby the magnet. So what you can do is you can set up a magnet like this, that's kind of like a U shape, and you've got north and south end. So in between the north and south end, there's a strong magnetic field. And instead of having a coil that you just move back and forth or move through and then take out and move through again and take out and move through again, if you turn it into a coil and rotate that coil, the 2 wires are going to be continuously moving through the magnetic field, and so it's going to create current through that wire. The only problem is, every half cycle, the direction that the current is going to move is going to change, because like right now the wire may be moving left, but then it's going to be moving right, and then it's going to be moving left, and then it's going to be moving right. So the wires, it's essentially moving back and forth in opposite directions, and because it's moving back and forth, the current that's created is first going to go one way and then going to go the other way. So that type of current is called alternating current. And I think earlier in the year some people had been asking, why do we use alternating current or direct current? How do we decide what it is? And this is a big reason why, is because the way that power plants work is by rotating these coils inside of magnets, and that's naturally going to generate alternating current. Okay, so let's look at a simulation that will help explain this. Okay, so for this simulation, this is a coil of wire that's hooked up to a light bulb, and here's a magnet. So if we take the magnet and we move it towards the coil, let me make the magnet a little bit bigger and stronger. Okay, so if we move this magnet, if they're both just sitting next to each other, you can see there's no light coming out of the bulb. if I move it away or towards, as I moved it towards, you saw the light light up, or if I move it away. So whenever I move it towards it or away from it, as long as I'm moving the magnet relative to the wires, charges are flowing through here and the light is lighting up. And if I move it back and forth quickly and with a long distance, the light will get really bright. If I move it really, really slow, you can see the light is just barely illuminating, just a little bit of light coming out. So this illustrates the idea that if we have these magnets and they're moving relative to the coil, then there will be current flowing through the wire. Okay, so back over here. So again, it creates alternating current because first you have to move the wire one way and then you have to move it back the other way. And that back and forth motion changes the direction of the current each time. As you saw in the sim, the electrons were first moving forward and then backward and then forward and then backward, alternating. Okay, now we're going to take a look at the mathematics of this alternating current. So you've got the voltage at a max value here, but then it goes down to 0 here. So when you're looking at power transmission, you've got the formula P equals IV, but the current and voltage are both changing on and off, on and off. So to calculate the total power transmitted, you kind of want to think about taking an average or an effective value. If the current would have been constant and if the voltage would have been constant at some lower value, you'd end up having transferred the same amount of total energy. And so it turns out that these lower values are 1 over the square root of 2 times the original value, which would be or times the max, I mean. To prove that it's 1 over root 2 for the current and the voltage, you can just look at this sine wave, and you can calculate the effective or average value of the sine wave. Using calculus, you can do an integral of the sine wave and find out that it's going to be exactly 1 over root 2 of the maximum value. So knowing that, we can multiply this 1 over root 2 times the voltage max and 1 over root 2 times the current max. And the 1 over root 2 times 1 over root 2 is just 1/2. So the effective or average power delivered is 1/2 of the max power, which is 1/2 of the max current and the max voltage. And so that's useful because you need to realize that if your wall socket is supposed to be 120 volts, are they talking about the 120 volts as the max value, peak value, or are they talking about the 120 volts as the effective value? So when you're calculating, how much energy you're getting out of the wall socket, you want to be making sure you're talking about the right values. Otherwise, you need to put in a factor of 1/2. So that's just a good thing to keep in the back of your mind. Is it peak values or is it effective values? Okay. So the next thing is, in the sim, we practiced moving the magnet near the coil of wire. But another option is to keep the wire still and change the magnetic field, either by increasing the strength of the magnet, or by decreasing the strength, or by moving the coil back and forth, or by moving the magnet back and forth. So there's lots of different combinations that you can do. The net result is any change in magnetic flux. So it doesn't matter whether the magnet is moving relative to the coil is moving relative to the wire, or perhaps both are stationary, but the strength of the magnetic field is increasing, which is going to cause more magnetic field lines to go through that coil. Any of those things will cause current to flow through the loop. So what the net result of that is this: a change in the magnetic flux. And the magnetic flux is the amount of magnetic field lines going through a given loop. So that has to do with the strength of the magnetic field times the area of the loop times the orientation. So for example, if you have a loop like this and you have magnetic field lines going through it, you can see that if you make the loop area bigger, more lines can go through. If you increase the strength of the magnetic field, that will be creating more magnetic field lines, then obviously more lines are going through. Or if you take that, you keep the size the same, and you keep the strength of the field the same, but you take that loop and you rotate it, at some point it's going to be rotated, and so it's parallel to the field lines and nothing is going through. And if you keep rotating, then it will become perpendicular and all the lines will go through. So if you rotate that loop, you'll be changing the amount of magnetic field going through it, which will generate current inside the loop. To figure out the direction that the current is going to flow, is it going to flow clockwise or counterclockwise, we have something called Lenz's law. Okay, and it says the direction of the current induced, okay, so the new current created in this loop causes its own magnetic flux, which opposes the original change. So this is a very kind of confusing thing to wrap your head around. Okay, so there's some magnetic field on the outside, okay, that's increasing or decreasing the amount of flux going through the loop. That's going to cause current to flow through this wire. But we just learned last chapter that if you have current going in a wire, that creates its own second magnetic field. So this new second magnetic field opposes the original change. So if the magnetic field was increasing, this new magnetic field will go against it in the opposite direction. But if the original magnetic field flux was decreasing, the new magnetic field will go in the same way to try to keep it at whatever its value was. It's basically trying to keep it stable. And so let me go to the next slide. There's a much bigger picture we can use to describe. So if the magnetic field is pointing upward and increasing, then we need the induced magnetic field to point downward. And so we can use our right-hand rule here, which is if we wrap our thumb in the direction of the current, our fingers will curl in the direction of the magnetic field. And it's hard to describe on a 2D thing. So in class, I'm happy to go through this. I have we can use any kind of big hula hoop or something like that to really visualize in which direction the current is going to flow around this loop. But again, just remember, the induced magnetic field opposes any changes in the current magnetic field. So it's trying to keep it stable. All right, so let's look at another simulation. Again, showing the generator. Okay, so let's take a look at this sim for how a generator works. So we want to create electricity using magnetism. And we learned that if you change the magnetic field or change the magnetic flux, it'll cause current through the loop. So right now, we've got a magnet sitting here, not moving, and we've got a loop sitting here, not moving, and so there's no current going through it. But if I can somehow either move this closer or farther, or change this or rotate this in some way, the magnetic field that's created over here will change, which will cause current to flow. So if I turn some water on out of this spigot, it's turning this is like a paddle wheel. Because this is turning, the magnetic field, it's creating a magnetic field. Let's show the magnetic field. The magnetic field is continuously changing direction. So you can see inside the loop right here, let's put this, wow, it's stuck. If you put it right here, the magnetic field is first going one way and then going the other way. And if you look at these charges, first they slide, they're going this way downward. And then after half a loop, they slow down, and then they start going back up the other way. So because this is oscillating, changing direction back and forth, it's creating a current that's back and forth in here. And you can see the light is pulsing on, off, on, off, on, off. And if you had your current generated at a low frequency, you really would see the lights go on, off, on, off. But if we increase the speed here, they're still going on and off, on and off, on and off. But it's at a faster speed, so you might not notice it. And if you turn it up really, really fast, it's on and off so fast that your eye can't really even notice that it's ever going on and off. And furthermore, if you have a tungsten bulb, once it gets hot, it's going to glow continuously. So even if you turn the current off, it keeps glowing for a split second later. And by the time it would have turned off, the current's back through it again the other way. And so it never actually shuts off. Okay. So this is the basis for creation of electricity in power plants. You've got magnets that are rotated near coils of wire, and that creates electricity in those coils of wire. Okay, so energy transformations in this simulation are kind of interesting to look at. We start off with water at a high elevation, so it's got potential energy of gravity. As it falls down, it converts to kinetic energy. It hits this and does work on it. The work causes this to spin, which gives this kinetic energy. Okay, this kinetic energy physically moves the magnet, which creates a magnetic field. Magnetic fields actually have energy, so now there's energy in the magnetic field, and that energy is then transmitted over to here, which causes these charges to move, which gives them kinetic energy and also potential energy electric, because they're moving through a magnetic field, changing voltage, gaining potential energy. When they travel through the light bulb, they lose electric potential energy and convert it to heat and light, and then that heat and light expands out. So there are a lot of energy conversions as we go from here all the way over to here. All right. So let's look at the last thing from this chapter, transformers. So a transformer is something that you see a lot of times on power lines, and it's used to increase or decrease the voltage. And so we talked about why is it important to transmit at high voltages, and the result was last chapter, and we said it's because you lose less energy when you're transmitting at a high voltage, because then you can transmit at a low current. And so having a transformer, a way to increase or decrease the voltage, is really, really helpful and useful. And so this is kind of how they work. You've got the primary coil on one side, which has loops of wire, and when you turn the current on and off, on and off, on and off, it creates a magnetic field that alternates back and forth here. And if you have an iron core that transmits magnetic field inside of itself really, really well, because it's a ferromagnetic material, then that magnetic field that's on and off or alternating in directions is going to be over here as well in this part of the iron core. Or you can even take these two loops of wire and make them concentric with each other so that they're around the same iron core. So you're going to turn on and off a magnetic field here, which creates current in this secondary wire. So this secondary wire has no actual battery or power source connected to it. Its created current, or induced current, is caused by the changing magnetic field from the first source. Okay, and so the power in has to equal the power out because energy is conserved, and so the voltage is proportional to the number of loops. And then you can kind of relate the number of loops to the voltage by using energy conservation and power conservation. So the number of loops primary over the number of loops secondary equals the voltage primary over the voltage secondary. So if you have 1,000 loops, 1,000 times more loops here than here, you'll have 1,000 times more voltage here than here, because the magnetic field is the same on both sides. So let's go ahead and look at that in a simulation. So, and that's transformer. If we have, let's just say real quick, if you had a DC power supply, even if I put this completely on top of it so that they're completely concentric, because the current is always going the same way, there's no change in the magnetic field, and there will be no current induced. So if we tried to run power lines off of DC, this is what would happen. There'd be no way to step up or step down the voltage. But if instead we change this to an AC source, you can see that since it's alternating on and off in the primary coil, it's changing the magnetic field back and forth. You can see, if you look real closely, these are changing between red and white, which means the field is going back and forth in different directions. And that's creating current in this secondary loop, which is then turning the light bulb on and off, on and off. The farther away I put it, it's still on and off, but not as strong because the magnetic flux over here is a lot weaker. We can change this by, I can increase the speed at which it goes on and off. I can increase the strength. If I make it stronger current at a high speed, this light will be on and off more often. Or if I change to a lower frequency, then this is coming on and off at a lower frequency. So you have an alternating current power supply creating current in the secondary loop, even though there's no battery over here. So this is an induced current. Okay, so let's close that. So note that it requires AC because of what I just explained. All right, let's summarize real quick what we've learned in this chapter. The basis here is that relative motion between any wire and any magnet is going to cause current in that wire. It could be a simple bar that has current going and then develops a potential difference between the two ends, so that can act as a battery if you connect something. Or it could be an entire loop of wire that's rotating or moving in and out of a field, which then creates current through the wire and lights up some device. So this is the basis for all electricity. Doesn't matter what type of power plant we are talking about, all of them eventually do this. So the different types of power plant, like a coal power plant, a hydroelectric power plant, or even a nuclear power plant, what they do is they all have different methods for trying to rotate these magnets relative to these wires to create current. So for example, in a hydroelectric, I think it's just the water traveling past as it falls, which is causing rotation like that one that we saw in the simulation. But then in a coal or a nuclear power plant, they burn coal or they use nuclear fission to create a lot of heat, and that heat is used to then boil water, which makes steam, and then the rising steam turns turbines, which are connected to magnets, which are near current, or which are near coils of wire to generate current. So all of these different power plants, except solar power plants, which are completely different, but all the traditional power plant types, they create electricity by doing this kind of rotation of a wire and a magnet relative to each other. So alternating current is the natural type of current to use in this case, because the current, in order to induce magnetic fields, you need to, in order to induce currents and voltages, you need the magnetic field to be changing on and off, and a direct current won't do that. And then lastly is we use transformers to step up or step down the voltage by using electromagnetic induction. And this is very, very useful for long distance transmission of power. We can step it up to many thousands of volts, transmit it to your house without losing very much energy, and then step it back down to 120 or 240 volts so that you can use it for regular household appliances. All right. The homework is going to either be emailed or on the handout that you've been given. Let me know if it's not there yet, and I'll make sure I get it posted. And make sure you fill out the form after the video.